everybody. Today I'm going to give you an intro to homogeneous coordinates. How many of you know them already? Okay, so then it's going to be smooth today. I'm going to do it for the first hour, roughly, and then the second part will be the exercise with setting up Octave, getting familiar with the Octave interface, the commands, and how to use it for the rest of the class. From the next week on, I will not be here during the exercise time. They will all just be Octave exercise. The idea will be that you will get on the web page an exercise sheet every week, and this will be due the week after that. It will work in a way that it will be available somehow between the lecture time and exercise time of a certain week. The TA will give you more info on when exactly this will be available. You will just take it from the web page, you will do the exercise, and you will submit the solutions to the tutors. And then they will correct them. And in the next week exercise session, they will explain the common mistakes. They will explain why something is not as some of you did, or anyway, some discussion on how you perform during the exercise. And then they will also explain how you should have done the exercise, so give you the solutions. There's no, so you will not be graded by the exercise directly, but it's good for you to do the exercise because they give you, so they allow you to better understand the theoretical parts and how to use them. It's very useful if you want to do some master project or some master thesis on the topic because you're already familiar on how to implement the concepts here. So see this also as a long-term investment for your future study here. And they might also clarify you some doubts on the theoretical aspects as well, okay? During the exams, which will be oral, I'm not going to ask details about the exercise, but I might ask some implementation insights or some tricks or some things that you will get familiar by doing the exercise. You also can learn them by just very deeply understand the theory, but normally these two things comes together, okay? So all clear? Any question? Okay, so regarding the topic of today, we're going to talk about these homogeneous coordinates, as I said, and the whole idea is that we are dealing now with a point in a certain space, and we need to find a way to mathematically modify, transform, and work with these objects, okay? And homogeneous coordinates are a tool, or let's say a way of representing spaces that allows you to have very elegant and simple way of computing transformations, modifying these points, considering potential orientation and potential, let's say, reference frame in space. And by reference frame, I mean like a point with a certain orientation, so that you can refer all the potential coordinates that you have in your space with respect to this reference frame, okay? Historically, homogeneous coordinates are used for a bunch of different topics. They go from computer graphics, computer visions, and the main power is to deal with what's called projective geometry. Projective geometry is something like you have a 3D world and you have, let's say, a camera, which is just one plane, and you want to know how this whole world gets projected on this plane, okay? But you can also use it for points that moves in space and gets transformed, and we'll see what are the different way of doing it. The idea is that in principle you can do these two things both in the normal standard Euclidean space, where you have just x, y, and z if you are in 3D, but then imagine you want to transform a point by rotating it and moving it. You will have some rotational part, which normally is multiplication of this point by a matrix, plus something. So you have two operations to take care of, a multiplication and an addition. If you use a homogeneous coordinate, all the transformation will be encoded in a single matrix, and we use this matrix to operate everything, and we'll see it later on. So the idea, in principle, how these are done is that you have also a way of, everything is on the concept of array. So you have a certain central point, and I think I have a figure which actually helps you understanding better, which is like this. So imagine you have a central, and everything is array that goes there, and then you somehow can imagine that your space that you're considering is this plane here. So imagine that you want to consider a 2D environment. You will have a plane, which is a 2D plane, and then your points in homogeneous coordinate will live in a 3-dimensional space, and they will define as rays there. And each of these rays will give you a point on a 2D plane, okay? And ideally, you can see the same from a camera. This is your 3D world, and this is your camera plane where the image gets projected. Okay? So that's to give you a visual. In practice, what we have is that we have coordinates defined like this, and we can define infinity, points at infinity in our space, and they will just be defined in a specific way because there will be just an array that doesn't intersect any plane, if you see the image before. And but the whole gist of it, the most important thing is that you will just use a single matrix to represent all possible transformation that you can do in a linear way, all affine transformation of this point. And a subset of this affine transformation is translation, rotation, translation followed by rotation, but you can also imagine you can make something bigger, so you can scale it up, or you can shear it, so like if you have a rectangle, you can make something like this, and so on. Mathematically, it's something defined like this. The whole concept of homogeneous means that if you have 2 points, x, and then you take a scalar and you multiply x by this scalar, they represent the same point in the space you're considering. Now, imagine that this is our x, and imagine that our x will be just something like this. So it's a 2D point, it has an x coordinate and a y coordinate. Now, if you multiply this, so I'm just going backwards to give you an idea, if you multiply this by any other scalar w, this will again give us the same point, and then we can have a different set of coordinates now, which is u, v, and w, that again defines the same point. Now, the trick is, once we have a vector in homogeneous coordinate, you can simply extract the real Euclidean point that you want by just taking the last coordinate, divide all the vector by this coordinate, and you get the x, y back here. Okay? As simple as this. And if you then want to go from this back, you just add the 1 here. For whatever we're considering in this class in terms of body that moves around, which is the pose of the robot, or if it's a point observed by the robot using a laser scanner, so everything which is not projective, so it doesn't come through a camera or some system that takes a 3D world and puts it on a 2D plane, we will always deal with points that have a 1 down there. Okay, that's like a canonical way of representing these points. When we deal with cameras, we will see how this W that's there comes into play. And there's somehow like the scale of how far this point is in reality if you just get it on the pixel plane. But today we'll just focus more on the generic of these points. Another interesting aspect is also rays at infinity, and we'll see it later. Now, this is what I showed you before. You can imagine that this point is actually a point in this 3D space that you don't care where it is. The fact that you put a 1 here, you basically are just taking the projection of this ray on the plane which has height 1. I just a definition by this. And this gives you the point in the 2D space that you are interested in. Is it everything clear so far? Any question? Okay. Now, by definition, by assumption, or however you want to call it, we say that the origin in 2D is the point 0, 0, 1, and the origin in 3D is the point 0, 0, 0, 1. So again, will be the point at 0, 0 or 0, 0, 0. And 1 is because we use this as a standard point in some way. If we want to get point at infinity, we just put a 0 there, okay? And you can see if you get from the standardization technique we've seen before, where to get the real point, we just need to take these coordinates and divide by this, you get infinity, no? Because you get something like a number divided by 0, and the limit of this will be actually infinity. So we are able to deal with infinity by just using another space. So, but just instead of considering our normal plane, we consider the other space. And the reason of this is also clear if you look again at the image by the projection. A point that has 0 as a third coordinate is a point that lies on this plane. So it's a point that goes either in this direction or in this direction or in this. So this ray will never touch this plane, and that's how you kind of get a concept or a notion of infinity in this way. Does it make sense? Okay. Now, why are they useful? As I said before, we use them because we care about transformation. And the idea here is that when we have homogeneous coordinate, we can express any kind of transformation that we want in this form. We have our new point, so the transformed point. It's equal to transformation matrix M, and we'll see now how this matrix looks for different class of transformations, and our original point X. One important transformation, so this P here is the space of all projective matrices. It's just a group, there's a lot of things on how to define transformation groups and so on, and this is one of like a big container for all potential projective transformation that we have. You don't need to go into the details there, but just to give you an idea why there is a P up there. If we are working in a three-dimensional space, we have that this matrix here is a 4 times 4 matrix, and it's normally also an invertible matrix. So you can get the invertible mapping between the two. So you can, once you have a transformed point, in some specific case, you can get to the original point back, okay? And if you want to do some translation, so we just take a point and we want to move it in the space, the transformation matrix looks like as this structure. It has an identity matrix on the top left. It has your transformation, your translation vector. So let's say I want to move the point 3 meters on the right and 2 on the left. This will be something like 3 here, 2 here, and since there is no translation on the z, I keep it 0 there, okay? So we just put the translation vector here. We have a 1 down here, and you will see for all non-projective operation, there's almost always a 1 down there. And now we have a 0 vector in this part. And again, since we are not projecting anything, we are not scaling anything, we're not changing the structure of the space, we're just doing rigid motion, this is 0. And again, this will be different for different kind of transformation. Similarly, if we want to do a rotation, just a pure rotation of the point with respect to the center of the axis. So if you have a point there, we want to rotate, this point will go in that direction then. We just have a rotational matrix here on the top left, and the rest is 0, okay? You notice this lambda here on the left. Any insight, idea why there is a lambda there? Do you remember what we said at the beginning about what's the definition of a point being homogeneous? So we said that if you have x and lambda x, they are actually the same point, no? So this lambda here is to say that this transformation from a homogeneous coordinate point of view are all defined up to a, let's call it scale, or up to a scalar, no? And they all define the same point, because you can increase or decrease, but you always are in the same point, because this lambda will act also on the lowest coordinate of the point, either here or here, and then you can renormalize them again. So to be formal, there is a lambda here, but in principle, you can also assume that this lambda is always equal to 1, and you just forget about the lambda. But if you want to be really formal in the whole framework, you need to consider that there is a degrees of freedom that you don't fix in this part. Okay? So, do you remember how rotational metrics are made? If you have a two-dimensional point, this is just the sine, the minus sine, cosine, and cosine of the angle. Okay? There is no ambiguity in that. You have just one potential rotation axis, which is the one that goes on the z direction of your plane, and you can only rotate in this direction here. So it's a very easy and nice way of defining rotation. When you go in three-dimensional spaces, that's not that easy, because you have not only, you can see that you can have three different angles, and the way you rotate, so the order on which you take the rotation on the different angles, actually impacts the final rotation that you go. And that's because you basically have somehow many degrees of freedom. One is you can choose by which axis you actually want to do a rotation, and the other one you can choose the amount of rotation there. If you use what's called Euler angles parameterization in a 3D space, so you say, I have three angles, one on the x, one on the y, and one on the z axis, and I want to define a rotation using them, that's how they will look like. So a rotation on the x-axis is just a two-dimensional rotational matrix embedded in a three-dimensional rotational matrix. And the same is if you want to do the y-axis or the z-axis. And you can see the parallel now. You can imagine that if this is x, y, and z, in some sense, this is exactly this if we don't consider the z-axis at all, right? Because rotations on the plane is always defined as a rotation on the z-axis. Now, if you want to have a full rotation in 3D, you can combine these three. So you multiply them, you take the one on x and y on z, and you multiply them. This is only one way of getting a rotational matrix in 3D. For now, I'll just give you this as an example, but there is a lot of different ways of parameterizing 3D rotations. And we'll see them in the class later on, how different parameterization can affect the matrix and all the properties. Yes?
About the orders of the RZ, R, Y, Rx,
Mm-hmm.
if we change that, is it have the different result?
Yeah, so the question is if changing this gets different results. Yes, it does. There is one thing, if you do, if you compute the rotation matrix in this way, that basically means using Euler angle, that's something called the gimbal lock. So what you will end up is that you imagine you can rotate in three directions. It can happen that by doing a certain rotation, you end up that two dimensions are actually the same. So that if you rotate on x on y after you do a certain rotation, you will get the same results. So one of them actually do not give you any effect. And you can also imagine that if I take, let me see if I can make something interesting. Imagine this is your point. So this is the point, this is the center. If I do a rotation on z, and then I do a rotation on y, I end up like this, and then I do a rotation on x, and I end up like this. If I invert them, and I do first a rotation on x, then I do a rotation on z, and then I do a rotation on y, I get up like this. So you see, you end up in different position because you change the space while you apply them. Okay? So this is what we've seen before from the rotation, and you can imagine that you can put a rigid body motion, which is a rotation and translation together, by just intuitively you will think about it. I put rotation here and I put translation here, let's just put them all together, and that's actually what really happens if you want to do a rigid body motion. This is telling you how much it rotates, and this is telling you how much it translates. And you can imagine this as exactly like applying the rotation and then moving the object around. And if you expand it, it will really look like you first multiply this from the first part plus t, that multiplies the 1 down there, so it's just like a absolute translation vector. Okay? Now this is the most important transformation if you have rigid body. So if you just consider bodies that can move rigidly in the space. And if they don't rotate, you put an identity matrix here. If they don't translate, you put a 0 there. So that's like the null, the identity element in the corresponding transformation class. Okay? If we instead go on more projective geometry, so when we go on real cameras or in general transformation that you can do, you have also a scaling. And you basically, the scaling, you can imagine that it's something that multiplies the rotation here. So if you just want to do a pure scaling, you put an identity matrix here, and you're just scaling, so enlarging the object or shrinking the object. You can also imagine that you can have any generic affine transformation. This is just any potential matrix, and all of them, they give you a different number of parameters. So if you do a rotation, this is defined by 3 parameters. With scaling, you add the 4th one. If you do the full affine transformation, you will have 9 here in 3D, and then plus you have 3 for the scale. So basically, every number in this 3 by 3 matrix is 1 parameter for your transformation. These are very generic transformation. If you deal with objects that are physically in a space and they cannot be enlarged or shrinked, they will never happen. But if you have cameras or if you have sensors that just take part of your environment and put them into a projection, then you might have something like this. Okay? Because imagine you are staying here, you see the same object in front of you, or like 10 meters in front of you, or 100 meters in front of you. This will just be seen as a scaled version of the same object in your camera. Therefore, you need to deal with some scale transformations in there. And if you also turn it, so you will see it skewed, because you will see that by the projection, like if you see a wall on the side of an image, you will see a larger part here and a smaller part there, and everything gets skewed in that. And this is a more generic affine transformation. Okay? So that's the idea where they come into play and where you why you need them when you deal with the reality and your sensor. Yes?
Dimension of the rotation matrix.
So the thing is this, the dimension of the rotation matrix, because this was the question, is normally is a 3 by 3 matrix, so it has internally 9 numbers, but all of these are constrained. So if you look at the structure of the rotation matrix, is something like, imagine this as an example, no? You have 3 real parameters, which are the 3 angles that you want to rotate. So if you really want to shrink it down. And this is, one parameter defines part of it, another parameter defines another part, a third one defines these things. You multiply them together, you end up with a 3 by 3 matrix, but there is some constraint inside that makes it that the real number of parameters is not the full 9, but it's just 3, because the others can be derived by the structure of the matrix. Okay? In general, okay, that's kind of getting a bit tricky on the side. In general, when you get, this is the rotation, in general, you over-parameterize a rotational matrix, because to avoid some problems, you put more parameters, so it's more stable in some occasion. It's hard to explain without practice, but there are some the gimbal lock I was telling you before. Now, if you put some certain angle configuration where you multiply this matrix, rotation of x, rotation of y, rotation on z, you end up that in some cases 2 axes gets aligned, and then if I rotate by one or the other, it doesn't change my final rotation. So it means that I lose 1 degrees of freedom in rotating the points in the space. To avoid that, sometimes it's useful to have more parameters, so to use 4 parameters instead of 3, and add some certain constraint in that. So you end up again in 3 parameters really, but you have more parameters to play with this with these problems there. That's what, for instance, I don't know, does any of you heard about quaternions? What? Quaternions? Okay. That's a way of defining, you know complex numbers, right?
Yes.
Yeah. So you can imagine a rotation in 2D as a complex number. No? That if you have the imaginary unit, so like you have a circle, no? And you can imagine you're rotating around this circle, and every complex number can be a point on this circle. Okay? Now quaternions are the same thing when you go in 3D, where you have a sphere and you have a vector pointing at the sphere. It's just that this is in a higher dimensional space. It's normally in a 4-dimensional space. But it's another way of generalizing complex number. You have, instead of one imaginary unit, you have three imaginary units, and the product of them is again -1, and the product, sum of them is -1. So there are other rules. It's a different algebra, but it's often used for rotations in 3D. And they have 4 numbers, and they have one constraint that says the norm of this 4-dimensional vector is 1. So you have 4 parameters with 1 constraint. Again, is 3 parameters, but you explicitly have them as 4. Okay? I don't know if it gets too complicated, but just ask and or send email, and I'll give you more pointers to how to get this information there. Getting back to the lecture, this is a table that summarizes probably most of the transformations that you can have in homogeneous coordinate when you have 3-dimensional space and then 4-dimensional homogeneous vector. We've seen translation. It's defined just by translation vector up here. These actually are in 2D, not in 3D. We have a mirroring, so you can flip around a certain axis. And flipping is just you put a minus in one of these 2 elements. So here is flipping around the y-axis, here is flipping around the x-axis. Rotation, we have seen it. This is a rotational matrix. Rigid motion is a combination of rotation and translation there. We have a similarity transformation, where by similarity means that we're just scaling it up and down and maybe rotating around and maybe translating around, but no more than that. And this basically means that the angles between the points are kept the same, but not the distances. We also can have what we can call it like scale difference, when you have a scaling which is different in different dimensions. So in this case, you can still see in some particular case that the angles are the same, but it's not it's not always the same, and it's defined by just having a diagonal matrix on the upper left part. We have the shearing, and the shearing modifies also the relative angles in your original object here. And it's defined by a shearing matrix, where you have a diagonal. In the diagonal of this matrix, you have 1s, and on the other side, you have 2 different values, which are normally the same, and this is the amount of shearing that you do in the different dimensions. You can also have a shearing in only 1 dimension, so if one of these is 0, you only shear like either on this direction, or you can shear in this direction. Yeah, that's exactly what is explained down here. We can have an affinity, or like an affine transformation, where basically we have any affine matrix here and then a translation there. Or we can have a projection, okay, which is the most generic transformation that you can have. And a projection is just, you can change everything in here, okay? And you can see these values down here somehow as, this can be seen if you have a camera, something related to the focal length of your camera that will change the thing, and this is like the vector on which the projection actually happens. But I don't think we're going to see any of these things in the remainder of the class, but if you did computer graphics and you have a 3D world and then you want to project this 3D world on the screen for a rendering, you will work on this kind of matrix there, okay? So we can also invert transformations. So if you have a point prime defined in this way, transformed to M, we can sometimes get back to the X by just inverting M. But M is not always invertible. It depends. So it's invertible for most of this, but it's not always invertible from the projection part. And you can imagine this makes sense because you go from a three-dimensional world to a two-dimensional plane, and then you lost the, in some way, the Z, no? So you kind of are losing how to get back to there if you don't have some information. So then it means you need to put some constraint on this matrix to be sure that you can reinvert it, okay? If you want to make a sequence of transformation, you can just chain them up. And you can see it also, normally, let's say I want to rotate the point, I do a rotation, then I want to translate, and this gives me a point, which is the rotated point, then I translate it and I do a translation and so on. But all these transformations are not commutative. So if you change the order, you also change the final point. Some of them commute, like if you just have translations, they commute, so you can switch them. But if you already put some rotation there, they do not commute any longer. Okay? As I said, motions is expressed in this way, and this is one of the most important transformation metrics that you should remember. When we use, let's say, full sensors, in a sense of sensor that measures the full space, like a laser scanner, or something that doesn't project and doesn't deform the space on the sensor readings, we will mostly use something like that. When we use cameras, we might get into the projection matrix, but not as deep as you will do in computer vision or you will do in computer graphics. So this is basically what I wanted to tell you today. Was brief on these homogeneous coordinates, but just to give you an idea or a refreshing if you've seen them already before. And to conclude, basically what you need to remember from this lecture is this set of points here. First, that homogeneous coordinate is a different way for representing points in space. It's you add another coordinate that allows you to use some mathematical tools in a different way and having easier computation. They are defined to be equivalent up to a certain scale, which is this lambda here. And of course, lambda must be different than 0, otherwise you just completely nullify the point. And you have simple expressions to do transformation. As you have seen, there's just mathematically just one matrix, and what you need to care is how this matrix is structured and where to put the numbers in there. But then once someone gives it to you, all the rest is just matrix multiplication. And we often use them for motions, so rigid body motions of points in space. Some pointers. There is, I think you should find this on the web page, otherwise you can look at it. There is a script, it might be in German, so I don't know how good for you this is, but if you need some further tutorial or info, lecture notes on homogeneous coordinates, just write me an email, I will try to find something. Otherwise, you can go on Wikipedia, there's a lot of information there, and of course there's also information on homogeneous coordinates. The wiki page is more than enough in a sense that you can skip a lot of things there. At some point it starts to go into group theory, operation theory, and so on. You can just completely skip all of that, but just try to get a gist on like some more info on that. So you can go as deep as you want once you start from there. Okay? So that's everything for today. There will be the exercise or the octave setup later on. Do you have any question? Also organizational, anything? No? Okay, then that's it, and good luck with the setting up of octave, and we'll see each other on Tuesday next week.